I'm John Lo Eliasi from Bachelor of Technology and Library Education, major in Home Economics 2. I'm the Chapter 12 reporter in climate change and tackle about the Earth movement around the Sun. And they have Earth moves in two different ways, which is rotation and revolution. And the first is rotation. The Earth rotates its own axis. Its axis is an imaginary line that passes through the North Poles and the South Poles. This axis is tilted at an angle of 23.5 degrees. The Earth takes 24 hours to complete one rotation about its axis. This is called one Earth day. The Earth travels 2,200 km per hour. The North Pole or the Northern Tropic and the Southern Tropic is equals in 25.5 degrees. The effect of rotation of the Earth. The rotate of the Earth causes day and night as the Earth rotates on its axis. Half of the Earth faces the Sun and the half of the Earth faces away from the Sun. The half of the Earth that faces the Sun will experience a day, while the half of the Earth that faces away from the Sun will experience the night. This image is example if magian kita sa sunrise or adlaw is kuan mo ni tawag sa tuaga ng day. If kuan man take man nag 24 hours sa nya ang kanang ang sa sunrise is makuan ta mo na day nya ang kuan na sa ang wala ko na sunrise mo gitawag og night. And they have different period between night and day is called dawn, and the period between day and night is called dusk. The second Earth moves is revolution. The Earth revolves around the Sun is called revolution, and the Earth revolves around the Sun is fixed path and it is called orbit. The Earth orbit is elliptical or oval shape. The Earth takes 365 days and 6 hours to complete one revolution, and the speed of Earth revolution is about 18 miles per hour. They have interesting fact. The Earth takes 365 days and 6 hours to complete one revolution, and the extra 6 hours accumulate over 4 years, and they are added as the day to the month of February every 4th year. So February, which usually has 28 days and has 29 days every 4th years. So this is called a leap year and has 366 days. The effect of revolution of the Earth. Most places Earth experience different season in a year. So you have three different factors causes the season. The revolution of the Earth around the Sun, the tilt of the Earth axis of rotation, and the tilt of Earth axis remain constant. The Earth experiences different seasons in a year, which is summer, winter, spring, and autumn. In December, the South Pole is facing the Sun, while the North Pole is facing away from it. So it is a summer in the Southern Hemisphere and winter in the Northern Hemisphere. In March, neither of the poles is facing the Sun. It is the spring in the Northern Hemisphere and autumn in the Southern Hemisphere. And the September, neither of the poles is facing the Sun. It is the spring in the Southern Hemisphere and autumn in the Northern Hemisphere. And in June, the North Pole is facing the Sun while the South Pole is facing away from it. So it is summer the Northern Hemisphere and the winter in the Southern Hemisphere. So the part of the Earth that is tilted toward the Sun gets the direct rays of the Sun and has summer, while the part of the faces away from the Sun relieves the heat from the Sun and so has winter. Twice a year, in March and September, neither of the poles is facing the Sun, and all parts of the Earth get roughly equal hours of day and darkness. At this time, places on Earth have seasons like autumn and spring, which are neither too hot or too cold. The Northern Hemisphere and the Southern Hemisphere experiences opposite season. For example, in December, Canada, which lies in the Northern Hemisphere and winter, while the The Australia in the southern hemisphere has summer, and the June in Canada experience summer while Australia experience winter. So the summer season months are hot and dry. The days are long and night and short. It many places river and lakes run dry. So sa Philippines mo ni gitawag sa tuag kanang El Nino gay kanang makuan-kuan ng kanang mga yuta kanang magliki-liki gani. Ug mao sa nay ganahan sa mga foreigner kanang magpa-init gani na ila kuan na term ana kanang magpasanbating sa kilid gay sa dagat. And the next is autumn season. Autumn leaves change color and start falling from the trees. Days that night are of the same length. The weather is pleasant. Kana ganing kanang mag-brown na niya mga tagak para mag kana mo na ikuan ikasunod na kay mag-ilis na sila kahuman diyan na kanang mag-ilis din na sila kanang kuan kanang mag-ilis sila kanang bagundahan gani. And the next is winter season. It is a very cold during winter. In many places, snow falls, trees lose under leaves. The days are short and the nights are long. So kani ngayong kunya winter season sa Philippines di mga kunya di man ikakuan kay sa diri sa tuwa. Kanang ang kaning kuan sa winter season kay noon kani sa kaparehan ng Canada ug Australia. And the last season is spring season. During spring, trees sprout new leaves and flowers bloom after the cold winter months. Bird builds nests. The weather is mild and pleasant. So para katugay kuan pagkahuman nato sa kuan gani. O katong kuan autumn season mo ni misunod ang spring season. So kanaging kuan makatabang ni kanang kuan spring season kanang nanay mga leaves gani. Kay makakuha ng mga kanang pareha ng mga animals like bird makabuhat sila kanang nest nyo kana sa mga taguanan nila gani. So natin mga timailhan kung unsa naman sa northern hemisphere o southern hemisphere na season. So sa March is the spring sa northern hemisphere, then the southern is the autumn, and the June in northern hemisphere is summer and the southern hemisphere is winter, and the September is in the northern hemisphere and the is autumn, and the southern hemisphere is spring, and the December in northern hemisphere is winter and the southern hemisphere is summer.
Good morning, everyone. My name is Ronald G. Maluya, and I will be the second reporter. My topic for today is the Milankovitch parameters and climate change. Understanding long-term climate change. What are the Milankovitch theory or the parameters? Developed by Milutin Milankovitch in the 1930s. The Milankovitch parameters are factors that influence the Earth's long-term climate, named after Milutin Milankovitch, who developed the theory in 1930s. These parameters describe how Earth's movements and impact solar radiation. Three key factors of affecting Earth's climate are 1. Eccentricity, changes in Earth's orbit shape. 2nd is the axial tilt, changes in the angle of Earth's axis. 3rd is the precession, wobble in the Earth's spinning axis. Now, what are these three? 1. First is the eccentricity. What is eccentricity? Eccentricity describes the shape of the Earth's orbit around the Sun. Earth's orbit ranges from almost circular eccentricity equals 0.005 to slightly elliptical eccentricity equals 0.0607. Variation in solar energy received between perihelion closest to the Sun around January 3 to aphelion farthest from the Sun January 4. and also changes the distance between Earth and the Sun during perihelion closest to the Sun and aphelion farthest from the Sun. Cycle duration 100,000 years. Next is the obliquity, the tilt of Earth's axis relative to orbital plane. Tilt varies between 22.1 and 24.5 degrees, with a current tilt of 23.5 degrees, with a cycle durations of 40,000 years. The impact affects the distribution of seasons, solar energy between influencing climate patterns. This determines how sunlight is distributed between the poles and the equator. A greater tilt means more solar energy at the poles, influencing climate patterns. Next is the precession. So what is precession? Precession is the gradual wobble of Earth's rotational axis. Cycle duration of 19 to 23,000 years. With the impact changes the orientation of the Earth's axis, affecting relationship between tilt and eccentricity, influencing the timing and eccentricity or intensity of seasons, which changes the orientation of Earth's axis relative to its orbit, influencing the timing of the seasons in their intensity. Now, let's go to the Milankovitch cycle. Eccentricity is Earth encounters more variation of the energy that it receives from the Sun when Earth's orbit is elongated than it does when Earth's orbit is more circular. A more elongated orbit leads to greater variation in solar energy. Obliquity or tilt of Earth's axis varies between 22.2 degrees and 24.5 degrees. The greater the tilt angles is the more solar energy the poles receive. A larger tilt increases polar solar energy. Next is the precession. A gradual change or the wobble in Earth's orientation of Earth's axis affects the relationship between Earth's tilt and eccentricity. Affects how axial tilt interacts with orbit shape, influencing seasonality. Next, let's go to the scientific debate. Early scientists dubbed the impact of small orbital changes. About small orbital changes, early scientists questioned how minor variations on Earth's orbit, axial tilt, and wobble could significantly impact the planet's climate. At the time, the changes seemed too subtle to account for phenomena like ice age, long-term climate shifts. Milankovitch lacked modern tools to validate his calculations. The lack of validation tools. In the 1930s, Milankovitch did not have access to modern instruments or computational technology to prove his theory. His calculation relied on basic mathematical models, which, though detailed, were insufficient to convince the scientific community. Mathematical modeling and cumulative effects were hard to prove at the time. difficulty in proving cumulative effects, the Milankovitch theory suggested that small consistent changes over thousands of years could add up to large climatic effects. This idea was hard to test or observe directly at the time, as long-term data on Earth's climate was limited. The scientific debate reflects the challenges of Milankovitch faced proving his theory due to limited tools and data. Next, let's go to the advances of science or in science. Over the years, advances in science provided tools and methods to revisit and validate Milankovitch theory. Advances in mathematics and computing allows the scientists to revisit the theory, improve mathematics and computing. Now, modern computing allows scientists to create detailed simulation of Earth's orbital mechanics and their effects on climate. Mathematical models could now account for complex interactions between eccentricity, axial tilt, and precision. Chaos theory showed that small changes can lead to large cumulative effects over time. The chaos theory. This theory developed in mid-20th century demonstrated that small changes in a system could lead to large effects over time. It supported Milankovich's idea that minor orbital changes could accumulate to, to drive in significant climate shifts. Milankovitch parameters are now considered significant in long-term climate changes. Advances in geology and paleoclimatology techniques like ice core sampling and sediment analysis provided long-term climate records. These records showed patterns in temperature and atmospheric composition that align with Milankovich's cycle. Advances in science eventually validated his idea, showing that Milankovitch parameters are key drivers of long-term climate change. Now, let's go to the summary and relevance of the topic. Climate change involved complex interactions between Earth and solar radiation. Earth's climate is shaped by how solar radiation, or energy from the sun, interacts with the Earth's surface and atmosphere. The Milankovitch parameters, eccentricity, obliquity, and precision, influence the amount and distribution of this radiation over long timescales, driving significant climate shifts. Milankovitch parameters provide insights into the historical and future climate shifts. By studying these parameters, scientists can explain past events like Ice Age and interglacial periods. These insights also help predict how Earth's climate might naturally evolve in the future, aiding in long-term climate modeling. Chaos theory highlights the importance of cumulative effects over time. Chaos theory shows that even small changes, like shifts in Earth's tilt or orbit, can accumulate over thousands of years to create significant climate effects. This principle underscores how the Milankovitch parameters, though subtle, have a major influence over long periods. Ongoing research validates Milankovitch contributes to the understanding of climate dynamics. Modern scientific tools and data have confirmed that Milankovitch theory accurately explains the natural long-term drivers of climate change. His work remains foundational in the understanding of Earth's climate system and its evolution. Now, let's go to the conclusion. Milankovitch parameters explain long-term changes in Earth's climate. This highlights that the variations in the Earth's oblique shape, eccentricity, tilt, obliquity, and axial wobble precision drive natural climate cycles over tens of thousands of hundreds of years. These parameters are essential for the understanding, like phenomena, the ice age cycles, and long-term shifts in the global climate patterns. Advances in science have strengthened the theory's relevance. Modern tools such as computer modeling, improved mathematical techniques, and geological data like ice cores have provided strong evidence supporting Milankovitch ideas. These advancements have made the theory more applicable and reliable in climate science today. Understanding these parameters is critical in studying the global climate patterns. Milankovitch parameters help scientists differentiate between natural climate variability and human-induced changes. They are crucial for understanding Earth's past climate, predicting future trends, and creating effective climate models for long-term planning. That's all. Thank you.
So, hi, good morning. I am Mayna Villegas from the Bachelor of Technology in Livelihood Education, major in Home Economics 2. So, I am going to tackle and discuss what global warming is, why does global warming occur, and its causes. What is global warming? Global warming is one of the major causes of environmental pollution and climate change. It means that there is a disproportionate increase in the Earth's temperature over a period of time. It is a completely dynamic system since the temperature varies constantly, but the solar energy is absorbed by the Earth, generating, as a consequence, the overheating of the Earth. So the global warming, a long-term warming of Earth climate system since the pre-industrial period, is primarily caused by human activities, primarily fossil fuels burning. This increases heat-trapping greenhouse gas levels in the atmosphere, leading to an increase in Earth's global average temperature by 0.2 degrees Celsius per decade. The largest human influence on climate change is the emission of greenhouse gases, primarily from burning fuels for electricity, heat, and transportation. The impact of global warming include rising sea levels, extreme weather events, and melting glaciers. The Milankovitch parameters seem to be part of the cause of climate change, though not the only cause. Some other factor seems to be needed. Today, as the world considers climate change and its implications on food security and national development, many nations are taking a deeper look at the science behind the issue. Most of the scientists who study climate change agree that the average temperature of the Earth's atmosphere has been increasing by over 90% in the latter part of the 20th century. What are the causes of this phenomenon? According to Rees from 2001. So there are two opposing arguments on the issue of whether or not this global warming is just natural. One side states that nature simply acting according to its laws with no reference to human beings and their actions is the main reason. For the purveyors of this belief, global warming will happen as naturally as the sun rises and sets. Meanwhile, the other side maintains that global warming is caused or greatly abused by the action of human beings. It lays the blame on the action of humanity, past and the present. An oft-cited fact to better understand global warming is the temperature of the planet versus the amount of carbon dioxide in the atmosphere. So in the graph below, the x-axis shows the year and the y-axis represents the amount of carbon dioxide or the CO2. In the atmosphere measured in parts per million or ppm, it should be noted that the amount of the carbon dioxide in the years before 1950 remains fairly constant but begins to climb afterwards. An important visual is the sharpness of the carbon dioxide increase around the beginning of the present century. Some scientists believe this level could reach an irreversible situation in which the heat and temperature of the planet will be unstable and unpredictable. It should be remembered as well that while carbon dioxide is a known indicator of global warming, it is not the only greenhouse gas to be concerned with. So why does global warming occur? Global warming is produced by the increase of temperature on Earth, resulting in great consequences that are represented in the Earth's atmosphere, where gases are emitted that produce the greenhouse effect and cause a great climatic change. The overwhelming scientific consensus is that human activities, primarily the release of greenhouse gases from burning fossil fuels, are the primary driver of current global warming. This warming trend is causing significant changes to Earth's climate system, with widespread impact on ecosystems, the human societies, and the planet's future. So let's go down here in causes of global warming. There are several causes that provoke global warming, which are divided into the natural causes and the man-made causes. The natural causes are produced according to changes in the Earth's orbital motion, the solar variability, and the natural events, such as volcanic activity. So the man-made causes are those produced by effects in which humans participate in this process, the increase of greenhouse gases due to excessive industrial activity, deforestation of forests and jungles, burning of fossil fuels derived from oil, natural gas and coal, and the burning of fossil fuels such as oil, the natural gas, and coal. So next are the consequences of global warming. The main consequences of global warming are those that we observe daily in the news. The hurricanes, the droughts, the floods, the fires due to the very high temperatures causing deforestation as well as lack of food and resources. Another major consequence is the melting of glaciers, changes in ecosystems, and the increasing danger of extinction of animals. So, the consequences of global warming are far reaching and complex, impacting every aspect of our planet and our lives, from extreme weather events and ecosystem disruptions to human health concerns and economic instability. The effects of climate change are already being felt and are projected to worsen in the coming decades. Urgent action is needed to mitigate greenhouse gas emission, adapt to the changing climate change, and build a more resilient and sustainable future for all. So let's go down here. The possible solutions to fight global warming. So first, we have to pay attention to the use of electricity in your home or in our home. Second, adopt recycling knowledge and habits. Third, we must plant more trees. Fourth, pay attention to the amount of garbage that we generate. 5. Use public transportation or bicycles to reduce the amount of gases emitted by cars. Lastly, raise public awareness about the importance of caring for the environment.
So now, let's talk about greenhouse gases. So greenhouse gases are specific gases in the Earth's atmosphere that can absorb and emit infrared radiation, a type of heat energy. When sunlight reaches the Earth, the planet's surface absorbs some of this energy and re-emits it as infrared radiation. The greenhouse gases such as carbon dioxide, methane, nitrous oxide, water vapor, and ozone trap some of this heat by absorbing the infrared radiation. After absorbing the heat, these gases re-emit in all directions, including back and forward the Earth's surface. This process, known as greenhouse effect, helps to maintain the Earth's temperature at levels suitable for life. However, human activities like burning fossil fuels and deforestation have increased the concentration of these gases, trapping excessive heat and contributing to global warming and climate change. The British engineer, physicist, and chemist John Tyndall quoted, "As a dam built across a river causes a local deepening of the stream, so our atmosphere, thrown as a barrier across the terrestrial rays, produces a local heightening of the temperature of the Earth's surface." This compares the atmosphere to a dam across a river. Just like dam makes the water behind it deeper, the atmosphere traps heat from the Earth, making the surface warmer. The atmosphere acts as a barrier, holding in heat and raising the temperature near the ground, similar to how a dam changes the flow and depth of a river. In the middle of 19th century, John Tyndall made important observations about the greenhouse gases. He identified that the most prevalent greenhouse gas in the atmosphere at that time was water vapor. Water vapor plays a significant role in trapping heat in the Earth's atmosphere. Meanwhile, Tyndall noted that the amount of carbon dioxide was very small, and it was not yet considered as a major concern. However, Tyndall was concerned about what could happen to the Earth's atmosphere if industrialization expanded. Industrialization, the process of transforming a primarily agrarian economy into an industrial one, involves in large scale of use machinery for production. The operation of these machines requires electricity, which in Tyndall's time was primarily generated by burning fuels like coal. This burning of fossil fuels produces carbon dioxide as a byproduct, releasing it into the atmosphere. At that time, manufacturing plants were not as widespread, and industries were not producing significant amounts of carbon dioxide. Therefore, Tyndall did not see the emissions of carbon dioxide as an immediate problem. However, he recognized that if industrialization were to spread and grow, the increase of carbon dioxide emissions could have serious long-term effects on the Earth's climate, potentially leading into global warming and changes in weather patterns. This foresight foreshadowed the concern we face today regarding the environmental impacts of industrialization and greenhouse gas emissions. By the mid-20th century, industrialization had expanded globally, especially after the World War II. This led to a significant increase in carbon dioxide emissions due to a widespread burning of fossil fuels like coal, oil, and gas to power industries, vehicles, and electricity generation. Charles David Killing, an American scientist, recognized the need to study whether the rise in carbon dioxide from human activities was affecting global temperatures. He wanted to understand the relationship between fossil fuel emissions and climate change. Keeling selected Mauna Loa Observatory, located on an extinct volcano in Hawaii, as his research site. This location was ideal because it was far from industrial pollution, ensuring accurate and uncontaminated measurements of atmospheric carbon dioxide levels. Keeling began continuous measurements of atmospheric carbon dioxide in 1950s. He plotted his findings on what is now known as the Keeling curve, a graph that shows the steady rise in carbon dioxide levels over time. This data provided the first clear evidence on how human activities were increasing carbon dioxide concentrations in the atmosphere. The Keeling curve became a landmark in climate science, demonstrating the link between industrial emissions and rising greenhouse gas levels. It also underscored the urgency of addressing human contributions to climate change. But how can scientists account for the correlation between the amount of carbon dioxide and the temperature? Is the temperature higher because carbon dioxide is higher, or are the values simply coincidence at this time in history? To answer to that, scientists use a combination of historical data, ice core samples, and modern measurements to demonstrate the correlation between carbon dioxide levels and global temperatures. Ice cores provide a record of atmospheric carbon dioxide concentrations and temperatures going back hundreds of thousands of years, showing that periods of high carbon dioxide are consistently associated with warmer climates. Additionally, experiments and models confirm that carbon dioxide traps heat by absorbing infrared radiation, a process known as the greenhouse effect. Is the temperature higher because carbon dioxide is higher, or it is just a coincidence? It is not a coincidence. Decades of research have established that carbon dioxide acts as a greenhouse gas, trapping the heat in the atmosphere and directly influencing global temperatures, while other factors like solar radiation and volcanic activity can also affect climate. The rapid rise in carbon dioxide due to human activities correlates strongly with the observed increase in global temperatures since the Industrial Revolution. Does correlation prove causation? While correlation alone does not prove causation, scientists have demonstrated causation through controlled experiments, physical principles, and climate modeling. For example, laboratory studies show how carbon dioxide absorbs and emits infrared radiation, and climate models simulate how increasing carbon dioxide levels lead to temperature rise. These findings confirmed that rising carbon dioxide levels are a primary driver of current global warming. Question: why does the average temperature of the atmosphere rise? What might have caused the unprecedented increase in its level? Well, the average temperature of the atmosphere rises due to the greenhouse effect, a natural process where greenhouse gases such as carbon dioxide, methane, nitrous oxide, water vapor, and ozone trap heat in the atmosphere. These gases absorb infrared radiation emitted by the Earth's surface and re-radiate it, warming the planet. However, human activities have significantly intensified this process, leading to an unprecedented rise in temperature levels. The primary causes include the burning of fossil fuels such as coal, oil, and natural gas, which release large amounts of carbon dioxide. According to the Intergovernmental Panel on Climate Change of 2021, fossil fuel combustion is the leading source of carbon dioxide emissions. Additionally, deforestation reduces the number of trees that absorb carbon dioxide, leaving more of this gas in the atmosphere. The Food and Agriculture Organization of 2020 highlights that deforestation has significantly diminished global carbon sinks. Moreover, agricultural practices, particularly livestock farming and rice cultivation, emit methane, a more potent greenhouse gas than carbon dioxide. Industrial processes also contribute to greenhouse gas emissions, further amplifying the warming effect. These human-included factors have intensified the greenhouse effect, causing the sharp increase in global temperatures observed today. Predicting the future climate is the challenging task due to the chaotic and complex nature of the climate system. The term chaotic refers to the fact that small changes in one part of the system can lead to unpredictable and amplified effects elsewhere, making precise predictions difficult. Scientists rely on computer models to simulate how the climate behaves and how it might change under various scenarios. However, the accuracy of these models depends on the quality and completeness of the data used to build them. For example, data on temperature, greenhouse gas concentrations, ocean currents, and solar activity from across the globe are necessary to create realistic simulations. Without reliable data, predictions may fail to capture critical details or regional variations. Moreover, Sparks and Hawkinsworth in 2019 point out that even when data is available, ensuring its quality is vital, as errors in measurements or inconsistencies can distort model results. Scientists also use tipping points as a framework for predictions. Tipping points are the thresholds in climate systems where small changes can lead to irreversible shifts. For example, the melting of the Greenland ice sheet could lead to a significant rise in the sea levels, or the collapse of major ecosystems like the Amazon forest could alter global weather patterns permanently. Predicting when these tipping points might be reached is particularly difficult, as the systems involved are highly sensitive to various factors. Overall, improving climate predictions requires more comprehensive data collection efforts, such as expanding satellite monitoring, deploying ocean buoys, and increasing international collaboration. For example, projects like the Global Ocean Observing Systems and the Intergovernmental Panel on Climate Change aim to fill data gaps and enhance understanding. These efforts are essential for making accurate predictions and developing informed strategies to address climate change.
Tipping points and chaos theory. Some scientists set tipping points, critical values where irreversible changes occur. Scientists have identified certain thresholds called tipping points, where small changes in the climate or environment could trigger drastic irreversible effects. These could be shifts in weather patterns, ecosystems, or even global temperature that once crossed cannot be undone. Once a tipping point is reached, a new state replaces the old one. Once a tipping point is reached, the Earth's climate or ecological systems may permanently change. For example, if global temperatures increase beyond a certain threshold, ice sheets might melt, leading to higher sea levels. Conditions after this change could be very different from the ones that existed before. In chaos theory, the Earth's atmosphere system may enter a chaotic region with high uncertainty. Chaos theory suggests that in complex systems like Earth's climate, small changes can lead to unpredictable, large-scale effects. As the Earth climate system becomes more sensitive to changes, for example, to rising CO2 levels, it might enter a chaotic region where predicting effects or specific outcome become very difficult due to the complex interactions and uncertainty involved.
Environmental and economic implication. Fossil fuels, major electricity source but lead to increased carbon dioxide emission. Balancing industrialization and environmental protection is essential. A balanced plan must consider all factors to resolve this debate. Environmental and economic implication of energy use. Fossil fuels as the primary energy source. Fossil fuels such as coal, oil, and natural gas dominate electricity generation due to their availability and cost effectiveness. However, their combustion releases significant amount to carbon dioxide, a greenhouse gas contributing to climate change and global warming. Virtue is balancing industrial growth and environmental sustainability. Industrialization drives economic development and job creation but often comes at the expense of environmental health. Activities like deforestation, mining, and manufacturing and degrade ecosystem reduce biodiversity and increase pollution levels. And laboratory is developing a balanced strategy. A sustainable plan must integrate environmental and economic priorities, ensuring both growth and ecological conservation. Renewable energy source, which is solar, wind, and hydropower, offer a promising alternative reducing emission while supporting long-term energy needs and governments, industries, and communities must collaborate to implement policies and practices to reduce reliance on fossil fuels while maintaining economic stability.
Future of science and modernization is a complex and multifaceted landscape driven by innovation and the pursuit of solving humanity's most pressing challenges. The future holds immense promise for scientific advancement driven by technologies like the artificial intelligence, quantum computing, and gene editing. Interdisciplinary collaboration is essential for solving complex global challenges, and open access and knowledge sharing will accelerate scientific progress. Modernization is a transformative force shaping education, the work, and our relationship with the environment. The digital transformation of education requires a focus on developing digital literacy and STEM skills. The future of work will be reshaped by artificial intelligence and automation, leading to job displacement and new opportunities. Sustainable solutions will be essential for addressing climate change. However, ethical considerations and societal impacts must be carefully addressed to ensure the benefits of this advancement. Privacy and data security are crucial, and promoting digital inclusion and equitable access to technology is essential. Unexpected consequences, such as the development of CFC, must be considered for responsible innovation. By embracing these principles, we can navigate the future of science and modernization with optimism and responsibility, creating a more equitable, sustainable, and prosperous world.